Hello and welcome to tribetopper.com.
And you're watching this video on important concepts of electrostatics. So we have considered a spherical shell which is charged, uniformly charged, and this O is the center of the shell, and R is the radius of this shell, the capital R, and it has a charge of plus Q. And of course, because it's a spherical shell, so the Gaussian surface where the electric field due to this charged spherical shell would be constant would be a sphere. So we have the Gaussian surface as this sphere here, where all the points on the surface of the sphere lie at the same distance from the center of the shell or from the entire shell, hence E would be constant. So we start applying the Gauss's law here. Now first thing, what is, if we just assume a small area vector ds, right, where your electric field is going out normally. See, this E represents the normal electric field lines and this over this small surface area ds. So then what is going to be your electric flux through the small area ds? So we have d phi, that would be equal to E dot ds, and because your E and ds vector, both the vectors are in the same direction, so theta is 0, hence you have d phi as E ds. That's over the small surface area ds. So what is going to be the electric flux through the entire surface? Therefore phi through the Gaussian surface, right? I will write here phi through the Gaussian surface, that means through the entire sphere that we have assumed around the shell. So that phi would be equal to integral of E ds. Now E is constant, cannot be integrated, so we'll take it, this is over closed surface, so E would be out, integration over ds. Integration of ds would just give us the total surface area of the sphere, and we know that is pi r square, so E into 4 pi r square. Now that's our equation 1. And also by Gauss's law, your phi is equal to Q upon epsilon naught, where Q is the charge on this shell. So from 1 and 2, equating the right hand sides, we get E into 4 pi r square is equal to Q upon epsilon naught. Therefore, what is E? That means the electric field due to the charged spherical shell at any point outside. See, the point that I assumed here is here, which is outside the shell. Okay, that's a point P outside the shell. So we find that E into 4 pi r square is Q over epsilon naught. So E outside the spherical shell is Q upon 4 pi epsilon naught r square. So we got the electric field at any point outside a charged spherical shell, and the field is due to that charged spherical shell. Now this is very clear that it varies inversely as the square of the distance. So the distance of the observation point from the center of the shell. If now I replace this small r with capital R, that means if I want to find the electric field on the surface of the charged spherical shell, then what would I get? So we have, if I put R as equal to capital R, that means I just bring my point here. So observation point P would come here on the surface of the shell. So I would get simply that E would become Q upon 4 pi epsilon naught into R square. So just small r would become capital R. So on the surface you have it capital R square. And if the third case, I want to find the electric field at any point inside the shell. So inside the shell, the charge is going to be 0, because we know one thing, that whenever we give a charge to a conducting sphere, it resides on the surface. So inside the shell, the charge Q is going to be 0, as it resides only on the surface of the shell. Only on the surface. Therefore, my E becomes 0. That means the electric field inside a charged spherical shell is going to be 0. So we found out the expression for electric field due to a uniformly charged spherical shell at a point outside the shell, at a point on the surface of the shell, and at a point inside the shell. So if we want to represent the variation of electric field with distance from the charged spherical shell, we get this kind of a graph. So ER inside the shell, so this line represents all inside the shell. As long as from the center of the shell to the surface, your electric field is 0. right? It's absolutely zero. Then on the surface, this represents the maximum electric field. So on the surface you have E max, that's q upon 4 pi epsilon naught r square. And as you go on increasing the distance, the graph represents that there is a exponential kind of a decrease in the electric field, because it's q upon 4 pi epsilon naught r square. So as this r goes on increasing from the surface of the shell, you go on getting a decreased electric field. So this graph is very important to show the graphical variation of electric field with the from a charged spherical shell with distance. This is a very important question. I hope you understood how to determine the electric field using Gauss's law for various shapes.
Please follow us on Instagram, Facebook, and Twitter at tribetopper.com.